Everybody, do we have any questions or concerns from last time? I received a few concerns thank you so much, from 3 people about quadrics, and I'll try to do my very best today on quadrics. There are people who express the concerns are right to be concerned, actually. Thinking back as a freshman, I myself had some problems with how I identified a certain type of quadric, and I think my professor at the time didn't take his time really explaining the conic sections you can get, the standard conic sections you get from cutting off a quadric with the standard planes, the XY plane, the YZ plane, the XZ plane. That would have been very useful to me. Later on, I had discovered the benefits of reading things on my own. That's why I'm always suggesting that you should read the book. If not the entire book section, at least the examples. Start example 1, example 2, example 3. Some people try to solve those on their own. I would not waste the time if I'm in a time crunch. I would just go ahead and read the solutions with no problem. And then when I get homework, and you will get some web work homework over the weekend, you shouldn't start over the weekend. I don't want to ruin your weekend, but maybe Sunday you'll get some web work homework, your first assignment, and then you will see what this is about, and then you will start working on it next week. Okay? When you are going to identify those problems, you'll say, oh yeah, she said that in class. So everything we do in class and at home is connected. Last time I answered.
Oh, where would you like us to do tonight?
Oh, I will collect it at the end. So at the end of the class, please everybody bring the extra credit and leave it on my desk, and I will take it off at home. And hopefully this weekend I will bring it. Coming back to section 9.7, which is the section that gives you the modalities in this review chapter 9. I say review in quotes because many of you did not have chapter 9 at all at different colleges. People here in Texas Tech and Calculus 2 had 9.1 through 9.5 most of them, or at least the instructors were supposed to cover those. In 9.7, what is challenging? Not the first things that we covered last time. So the most beautiful things that you saw were the model of the ellipsoid, and the particular case, which was the sphere. And could any of you remind me what the general standard equation of the ellipsoid is?
X squared over B squared equals Y squared over B squared equals C squared over C squared equals 1.
Very good. Now, do we have a name for those ABCs? We don't call them ABC anymore, right? We are in college.
Major axis, minor axis,
major semi-axis, because it's just the length of half of that axis. So I'm going to go ahead and draw the favorite shape of the Texas Tech Stadium. I'm going to write the equation. I noticed on the videos that it's hard to see the red, but I will do my best. X squared over A squared plus Y squared over B squared plus Z squared over C squared equals 1. And last time we were just talking that if you take C to be 0, you're going to get an ellipse of major and minor semi-axis A and B respectively. And I'm going to draw X here, Y here, Z here for the axes. So the A, what is the A? Is the distance from the origin to this point. So I'm going to call that little A, I'm going to call that little B, and the little C will be this guy from here to here. If I would want, for example, to draw an ellipse as a cross-section, which corresponds to what? To y equals 0. I would have what? I would have to look at that wall, right? Considering the corner that you have here in the left-hand side would be just like x-axis. The video doesn't see those z here and a y-axis along this edge. So if the y-axis comes towards me, like that, along this edge, then I have y equals 0 corresponding to this ellipse. And indeed, I should be able to draw better, and I apologize that I didn't do that job. Now, what is my technical mistake in this picture? Could anybody tell me, besides the imperfection of the lines, I should draw a dotted line, the one that you don't see in perspective is behind, right? Okay, if A and B and C are the same, we have a sphere. A equals B equals C will be what? Let's go that big R, and then we are going to have the sphere x squared plus y squared plus z squared equals r squared. So far, so good. Everybody happy with the ellipsoid? It's something we played since we were small. Whether we played football or we played soccer, we were happy with them. And it's time to say goodbye to them. And I'm going to move on to something else, which we may have in part discussed last time, but not so much, to hyperbole. You say, oh my God, hyperbole, that sounds like a mouthful. It does sound like a mouthful, and you have two very important standard types of hyperbole. I'm going to write the equation of one of them, x squared over a squared plus y squared over b squared minus z squared over c squared minus 1 equals 0. What I would want you to observe, because it's going to serve you a good purpose later, is that we have plus, plus, minus, minus. An alternation in signs. We have two pluses and two minuses when it comes to moving all the terms to the left-hand side. So if I am to move all the terms in one side, observe that I have this plus, plus, minus, minus thing. Why does that matter? We will see later. Now, I'm gonna, yes sir?
Could it be x squared over a squared minus y squared over b squared plus z squared over c squared over x squared?
Okay, that's exactly what I was trying to tell you, that if you have plus, that would be an ellipsoid, and we already know that.
But
right?
The y squared was minus.
If this were plus, you have a different type of hyperboloid. This is does anybody know one-sheeted, respectively two-sheeted? Which one is a one-sheeted? I was getting that. Which one is a one-sheeted hyperboloid and which one is a two-sheeted hyperboloid? So my next equation was, for comparison, x squared over a squared plus y squared over b squared minus z squared over c squared and plus 1 equals 0. Let's see what kind of animal that is. And he said, could it be? Absolutely, he's right. There is some magic thing that happens here. You have plus, plus, minus, plus. And you say, okay, wait a minute after that. If I multiply by a negative 1, the whole equation, how does it count that I have 3 pluses and a minus? I can have 3 minuses and a plus. Yes. So you have an uneven number of pluses and minuses, and that should ring a bell. Or an even number of pluses and minuses like you have here, and that should ring a different bell. What are the two bells that I am talking about? One represents a certain type of surface, the other one represents another type of surface. I have to learn by discovery. When I was taught these things, I was a freshman, very naive freshman, and I was trying to memorize because I was told to memorize. Take the equation, memorize the picture. That's the wrong way to learn, in my opinion, after 20-something years of teaching. We have to understand why a certain picture corresponds to a certain type of equation. If you don't know which one is which, then you're going to be confused, and for the rest of the course, you're not going to know much about quadrics, or this type of quadrics. Let's see what we are going to have. The magic thing is look at cross-sections. Does the video see me? Cross-sections, magic ones. Z equals 0 is one of the most important ones, and then z equals 0, and then y equals 0. And let's see what we have, what those cross-sections will be. That first one will be a conic, one of our old friends. What is this, guys? X squared over a squared plus b squared, y squared over b squared equals 1. It's an ellipse, right? Okay, so along the z equals 0, I'm going to have an ellipse, something like that. Imagine the surface will have this type of equator. And then for x equals 0, where is it? Okay, x equals 0 plane is this one, right? So in x equals 0, I'm going to have what type of conic? Oh my God, that's why I had to review. See, that's why I had to review those things with you guys last time. It was not that I wanted it so badly, but it was that we needed it. It's a standard conic parabola in the YZ plane. So if this is the YZ plane, it will look like that. Right? So I should start drawing. Do you see me video? Yes. So I'm going to have X, Y, and Z. And I'm going to have an ellipse over here. It's an equator. And in the YZ plane, I should follow my preaching from last time. Practically, this is A, this is B, and let's say this is C, and then I should draw that magic what? Rectangle, and after I draw that magic rectangle in the YZ plane, I should draw the asymptotes, and I know the first branch has to do what? Come from paradise. This is the asymptote, infinitely close, right? Come from paradise, kiss this point here, kiss the vertical line here, and go back to, I'm not going to say to where, asymptotically to the oblique asymptote. Okay? Alright? Yes, sir.
So that's two-dimensional?
That is a two-dimensional object. It's only one branch. I'm going to go ahead and draw the other branch, which if I can. Guys, you have to forgive me. Forgiveness is important in life and also in mathematics. I don't want to do it. I cannot draw perfectly well. These two guys should be perfectly symmetric, but I feel bad, so I'll do a better job. Okay? And I really appreciate that all the technology that's out there on the web, like the Khan Academy and so on. I'm going to send you some videos from Khan Academy. I'm going to also send you some interactive gallery of quadrics that was done by the University of Minnesota. Very beautiful, with Java applets, every such quadric. You can click on it and rotate it. Some of this interactive art is available in the textbooks ebook. Actually, there is a section. If you have an access code, you have an access code to your book. Through that access code, you can get to an interactive gallery of pictures. But we don't have all the quadrics there. So rather than sending you there, I can send you to a web link from University of Minnesota where they have an interactive gallery of quadrics. You can click on any of these quadrics, rotate them, look at their cross sections, and they will show with different colors the ellipse. They hyperbolize the section, the red things, and they add different colors. And then the other one, the other ellipse will be also like that. So instead of this, you will have one like that with different semi-axes. What exactly do you have when you put y equals 0? Yes, sir.
So by setting like the individual terms, x, y, z, 0, you can see what it looks like longitude and short lines, so you keep filling with the other longitude.
Right, because y equals 0 would represent what? The intersection of your surface with the plane y equals 0. And the plane y equals 0 would be this one. So I want to see where my surface intersects this wall. And where does it intersect that wall? I'm going to have in the conic x squared over a squared minus a squared over c squared equals 1, which is yet another hyperbola that looks like that. Are you guys with me? On that wall. So I can project it to that wall, but I'm here, right? So this is the one that you would have over here. I should have used a different color. One of the other authors of the textbook was saying to me, "You draw well, I cannot draw." That's why I write books. I don't know about that, but I'm not drawing well. I'm just trying to give you a sketch, an idea of what this water tower looks like. And what is magic about it is something you don't see in the picture. I may come and bring you a model somehow, either a virtual model by email or a real model, to see that this surface called one-sheeted hyperboloid is actually a root surface. It contains lines, and you will say, how in the world does this contain lines? Well, if you look at infinity, these almost look like lines, the branches of the hyperbola. Why? Because they come infinitely close to lines. They almost look like lines, but that's not the reason why. So you actually have families of surfaces, families of lines that in motion describe this surface. I'm trying pretty good at this dance. I'm not very good with it. Anyway, you have two families of lines which in motion describe this surface. And I should be able to move the elbow in a sort of elliptic motion, but I cannot. It's actually a way to describe this one-sheeted hyperbola. The thing is, one of our professors, this is a funny story, I hope he never finds out, or maybe he should. He sold a house to a friend of mine, a little house by Ransom Canyon, or was it, it's the other one, what's the other one, the Buffalo Springs Lake. And he had this tool, the learning tool, which is a stool. What? It's a little stool made of bamboo. There are these long, straight sticks made of bamboo that are all put together, and it certainly looks like, I cannot draw it, but practically, yeah. So it looks like that. I don't know if you've ever seen it. It's perfectly symmetric, and this stool is so nice. And I offered my friend, I knew exactly who got it and where it was coming from, and I offered him $50, and he said, take it for free, and I'm really happy because I was ready to offer $100 for that. It's a one-sheeted hyperboloid. So my friend, who is a car mechanic, asked me, he's also Italian, so we speak Italian. He's many things. So Australian, Italian, South African, American. So I asked him, and he said, oh, by the way, what the heck is that? And I said, this is, in mathematics, is a one-sheeted hyperboloid. And he said something bad, and I said, okay, don't just stop it. Okay, mathematics deserves respect, and you don't know, if you don't know what that is, you just keep it to yourself. But it's really beautiful. This kind of is also light. It's made of bamboo. And these sticks are together. You can even imagine them in motion, one after the other. They're so beautifully put together. A hot extra credit homework. Yes, sir.
What do you mean by one sheet or two sheet?
So, we will see next. This is, looks like more or less like a tube, right? But it's only in one piece. It's not disconnected. The other one will be disconnected. It will be consisting of two different sheets. And I'm going to show you. So, the sheet we were talking about is this one. The other one is practically one sheet and another sheet, both of them infinite, but completely disconnected.
And then, so, for example, on this one, if the y squared, if that term was negative and the z squared term was positive, would it still be considered a one sheet hyperbola?
Yes, sir. And it will be, you're just changing. Exactly. So somebody can give you any combination. Guys, look at that. X squared over 4 plus z squared over 9 minus, very good question, minus y squared over 7 and plus or minus 1. I'm talking one-sheeted minus 1. Okay, this is still a one-sheeted hyperboloid. What is different? Can you tell me what's different? This is, the y-axis is different. The y is different compared to these two.
Is it rotating?
So instead of z-axis in the middle as a rotation axis, you have the y-axis. Very good. All right. So very good question. You are heads up to me. I will try to get a little bit faster in that case. In these two-sheeted hyperboloid, it's a little bit harder to imagine what it looks like, but I'll try to do a good job drawing. First thing you see when you try z equals 0, you get a headache immediately. Well, you should. But what happens when you try to put z equals 0? You see why? How is that possible? That's not possible. A square plus 1 equals 0. That's complete nonsense. It has absolutely no solution. So you have no intersection at the level of z equals 0. And actually, if you move a little bit up and a little bit down from the floor, you're going to have no intersection for a while. And you may want to think what that y element may be. So then you're thinking, okay, I don't know intersection empty set, but then I hope to get some cross-sections in other cases, like y equals 0 should give me something beautiful. And it does give me something beautiful, which is x squared over, let me take a black one, x squared over a squared minus g squared over c squared plus 1 equals 0. And you say, oh, wait a minute, I don't like this. I can, if I shift this guy to the right, you have to be a little bit creative in mathematics, then I'm going to have the same thing as z squared over c squared minus x squared over a squared minus 1 equals 1. Okay? So you say, okay, so this must be some sort of hyperbola as well. And how about the other one? I'm going to leave it up to you to go home and experiment and draw these hyperbolas. They will be, if you look at the xz plane, what type of hyperbola would be that? If xz is like x and z, look at my arms, cannot be like that. Your hyperbola has to be just the conjugate. Oh wow, so instead of these branches in the actual plane that you're looking at, you are having these branches. Right? Okay, you can go ahead and think about this at home and experiment. You can also take x equals 0. Who tells me what I have when x equals 0? I also have the same kind of stuff that drives me crazy. Y squared over b squared minus z squared over c squared equals minus 1. What is it that I hate about it? It's not the standard hyperbola. I have to multiply again by a minus 1. So when that drives me crazy, I'm going to multiply by minus 1 by putting a plus, and a minus. And what is it that I notice again? That I'm getting c squared over c squared minus y squared over b squared equals 1. Is that in the standard orientation of the plane yz? Who the heck is the plane yz? This plane. Y is on the bottom, z is going up. Would I have it like this? Like this? No. Again, I would have, if it were y here and z here, I would have a standard hyperbola in the yz plane oriented like that. But unfortunately, it's not the case. They are swapped, so I'm going to have the conjugate one. So in both cases, the two hyperbolas are going to look different. And I'm going to go ahead and erase here. And I'm going to let you go home and yes.
Question on the hyperbola, how do you know if it's if they're vertical or if they're horizontal, like based on the equation?
Okay, we said that last time. It's okay. So assume that this is xy plane, right? If you have x squared over a squared minus y squared over b squared equals 1, the vertical asymptotes will look like y equals plus minus p over a x. You guys with me? That takes a little bit of work. That would be who the vertical asymptotes will be, who the oblique asymptotes will be. And then I'm going to have, for these oblique asymptotes, I'm going to have the standard hyperbola that looks like that. Okay? What if I put a plus here and a minus here? Say it again, Magdalena. Put a plus here and minus here and keep equal to 1. Then I'm going to have the conjugate. Right? So in my case, to make a long story short, because I really don't have that much time, I would like you to continue that at home. You are going to have two sheets, separate sheets, that continue to infinity. What are these branches? The black branch, I don't like it black. Let me make it red again. What is the equation of the red double branch? Tell me again. It's the one you obtain by making x equals 0. When you get y squared over b squared minus c squared over c squared equals minus 1. Or, if you wanted it in standard form, you write it z squared over c squared minus y squared over b squared equals plus 1. So, if you have a little bit of time, go home and try this by hand. What if you don't want to do this by hand? You hate to draw, you cannot draw whatsoever, not even as bad as me. Then I'll just send you that link for the gallery of quadrics from the University of Minnesota, and you're going to see them in action, they can play with them, see their cross sections. There is another cross section for x equals 0 that I mentioned today, which was this one. And if I were to draw that, then you have to wish me luck. For x equals 0 I did it, but for y equals 0 I didn't do it. It would be this one. Then I would have to draw in a particular color, and it would look like this branch that you see, this part you don't see, this branch you see, this part you don't see. It would still be, okay, it's very hard to mimic this with my hands, but be one branch here, one branch here, and the whole thing rotated and the semi-axis will change. So, really looking weird things. Now, I want one thing from you, and maybe you should you do it now? I think you should. Think about it now. How much space is there from the vertex of this sheet to the vertex of the other sheet? Exactly what is the dimension from the origin to this peak, and what is the dimension from the origin to this peak? Y over 2?
Or is it just C?
It's C. Why is it C?
Because
if x and y are 0, right? Are you guys with me? I'm looking at this line. X and y should be 0. I'm going along Z. Where do I have an intersection? When Z is plus minus C. And when Z is plus C, I have it here 0, 0 plus C and 0, 0 minus C. And actually, you can rigorously prove that there is nothing in between. You can actually take any plane that is between z equals minus c and z equals c, you're not going to intersect the surface. Alright? And this is what we call, tell me again, I told you there is no school for that. Two-sheet hyperboloid, it's a disconnected surface. It consists of two infinite pieces. So again, if somebody asks you in the exam, and it happened before, we had problems like that in web work, we still have them, you're going to get one, and in other examples in the book exercises, how do you recognize a hyperboloid from just looking at it? It has to have x squared, y squared, z squared over some numbers, and the 1 with plus or minus. The signs matter. If you have two pluses, two minuses, when you move everything to the left side, then it's a 1. It's a 1 sheet. If you have three pluses, a minus, or three minuses and a plus, then it's a different kind of animal. It's a 2 sheet. Okay? Alright. The thing is that for extra credit, you interrupted me when I said extra credit, and that's fine, but I want to come back to it. Maybe you're up to the challenge. Prove that the one-sheeted hyperboloid is a ruled surface. It's actually ruled. A one-sheeted hyperboloid is a ruled surface. That is a surface generated, that is, i.e. as in Latin, a surface generated by lines in motion. Actually, you have generated by two separate families of lines, straight lines. And, or but, I don't know, versus, how shall I say versus, the two-sheeted hyperboloid that is not a ruled surface. I once had a genius in my class, and every now and then I have a bunch of geniuses in my class. And after thinking for like 5 minutes, he said, I think I know why that is. I think it has to do with those pluses and minuses. And I said, why do you think that is? And he said, wait a minute, plus minus, plus minus. It's like a pattern that my high school teacher taught us. He said, your high school teacher must have been good. Where did you go to high school? Not because you could. And the pattern that he saw from his teacher was very funny. Actually, he was right. His teacher showed him if you have x squared minus y squared plus z squared minus 1 equals 0. Do you remember this kind of little exercise? Can you split into two groups of terms and write the sum of the squares as a product, sum and difference? So he played around with those a lot. And he said, you know, the fact that you have plus minus reminds me of high school, and I used to be very good at that. And then he went ahead and said, what kind of hyperboloid that could be? That would be a one sheet, because it's two minuses, two pluses when you look at that. So he went away and said, x plus 1, x minus y, plus z plus 1, z minus 1. The guy was smart, really smart. And then he said, what if I split? I don't want to give away the clue, but I'm always very, very good at giving away the clue. When I buy gifts for my friends, even here in the department, I sort of give them a clue that I want to buy a gift of a certain sort. So I completely spoil the surprise. I don't want to spoil your surprise. So the guy, based on the idea that he had, that was an idea, very simple, but the idea of a genius, he said, I think at this point I can prove to you that we have lines inside. And I said, what the heck? Yes, ma'am, because such a proportion like a multiplication equal multiplication, maybe you can write it as x plus y, x minus y, 1 minus z, 1 plus z, and I said, stop. At this point, I said, stop. You are solving the problem for everybody else. So he said, oh, from on I know how to get the planes. The intersection of a plane is a line. Your rule surface is a rule surface. That one sheet, it must be a rule surface, must contain a family of lines. I know how to get it. So he said, stop. So I don't want to tell you more because you have to find those families of lines yourself. Okay? There are two ways to arrange that, and you get to those two families of lines that generate the surface. You cannot do that for the two-sheeted hyperboloid because if you're good at class here, it's goodbye. You cannot factor out in real numbers the z squared plus 1. It's bye-bye. Right? Okay. Now, coming back to other surfaces that are important to us. You've seen part 1. Let's see what have we seen in part 1. We've seen an ellipsoid with a sphere as the most common and typical example. We talked about last time center and radius of the sphere. In part 2, we saw hyperboloid of one sheet and hyperboloid with two sheets. We saw the difference between them. Now, part 3. This is something that is a little bit easier, hopefully, to draw and to understand. And you've seen that before many times. Something that looks like a single z isolated. So it's going to be a graph of the form f of xy, where f of xy is of the following shape. A squared over a squared plus y squared over b squared. A and b are positive. What the heck is that? When I was asked what that is, I was 18. First time that I saw that. And I just replaced mentally A with a B and B with A with a 1 and B with a 1. And I said, z equals x squared plus y squared. I don't know, but it looks familiar. Okay. So I start thinking, and then somebody told me there is a different one that you have. What if you have z squared equals x squared over a squared plus y squared over b squared, which is looks a little bit similar. But it's different. It's different in nature. And I thought, okay, let me try and draw, because if I draw, maybe I find all the answers by drawing. And sometimes in life you find lots of your answers by trying to imagine things, draw a diagram, visualize them somehow. So if z would be 0, you only have one solution, which would be x equals y equals 0. So you have the origin, and that's it. Now, do I say that z equals positive? No, but it's implied. Why? Because this whole quantity must be either 0 or positive. It's greater than or equal to 0. So I'm only looking at the upper part. Above the floor. Everything is above the floor. But if I take other nice values, in case my a and b would be equal or equal to 1, doesn't make much difference. Z equals x squared plus y squared is going to be something nice. In the sense that at level z equal to 1, I'm going to have a circle x squared plus y squared equal 1. Somebody pick z equals 1 for me. And I'm going to have that here. And then I'm going to have at z equals 4, I'm going to have x squared plus y squared equals 4. I have a long plane in the sun. So how big will the radius be? 2. So I'm trying to respect the proportions, not say anything too deformed. And if I am to draw many circles, one on top of the other, by continuity, I'm going to get this beautiful, it looks like a cone, but it's not a cone, actually. It's a paraboloid, right? It's a paraboloid. And it's a, how do we call this type of vase? In this case, it's an elliptic paraboloid. But if A equals B, it's going to be a circular paraboloid. Because you will have cross sections at the horizontal planes being ellipses if you deal with this equation in general, A equals B, or if A equals B, you're going to have circle after circle after circle after circle. Have you seen one of those lamps that are made with circles of different dimensions and you put threads between the circles and hang them? Yeah, they are mostly made in Asia. They're extremely beautiful. And then if you use white fabric or something, you hang them, they give you a very nice calm atmosphere in that light, neon lights in the room. So you can imagine that bunch of circles for the circular paraboloid. They are called level curves. So what the heck is a level curve? A level curve you will learn in chapter 11, but I can anticipate a little bit. Okay, the set of all xy values with the property that f of xy equals a constant. Okay, so if you were to draw these, they would be circles in plane, and they would be just the projections of these circles from the surface to the plane. The ones I talked about, the circle of radius 1 corresponding to z equals 1. Projected down, you have the unit circle. For z equals 4, you get, what did we say you get? X squared plus y squared equals 4, radius 2 and so on. So if you were to be, this is the eye of God, or whatever it is here, I don't know, please, external observer, you see these concentric circles on the floor. These concentric circles on the floor that are the projections of the circles in your lamp. Okay, this is the source of light, and everything projects shadows. Those concentric circles are called the level curves. And we will see those again as an obsession in chapter 11. Alright, now this one looks similar, but it's sharpened. And I don't know, the waffle cone, the ice cream cone you have is more paraboloid, because if you look at those waffles, the ones at the mall especially are not sharp. They don't have perfect straight lines and a point of vertex. It's more like a paraboloid. But this would be a perfect cone. A cone that looks like that, that's the vertex. And it would be a double cone, moreover. And you tell me why you have a double cone. Why do you have the upper part and the lower part? Because it could be positive or negative, and for the negative part you get the exact opposite, the symmetrical part. So we call that a cone in practice, but it's not a cone, it's a paraboloid. If you go to an ice cream shop and say, an ice cream cone, waffle, whatever, it will say, give me a paraboloid, although it looks like a paraboloid. Right? Alright, so we have some very important surfaces that we talked about. But there is yet another type of paraboloid that is very important in our lives. And living in Texas, you cannot just neglect this. You cannot say, I don't want to know about this surface, it doesn't interest me, I'm giving you some hints. So assume that instead of this beautiful z equals what was it, guys? X squared over a squared plus y squared over b squared. You erase this plus and you put a minus, and you call that, well, for like a scientific term of a plant, Latin name of a plant. It sounds sophisticated, but in reality it has such a nice, funny name. such a suggestive name later on. This should be a what? A paraboloid? What kind of paraboloid? Oh my God, sounds like a monster. Hyperbolic paraboloid. Say it again, Magdalena. Hyperbolic paraboloid. Hyperbolic paraboloid that looks like a monster, but it's not a monster. I'm going to try to make A and B to be one for you to enjoy them. And so I'll erase this picture and I'll try. I cannot promise anything, okay? I'll try to draw z equals x squared minus y squared from scratch. And this is the picture to start with. That's the origin, that's the x-axis, that's the y-axis, that's the z-axis. And if I take z, okay, first of all, let me take x to be 0. Let me be a discrete girl, like I haven't been before. But if I were to explain x equals 0 first, and take the intersection, this is sine intersection with my surface, sigma. Sigma is my surface. The Greeks love that. Okay. To use letters as symbols for mathematical objects. You saw that I prefer pi for a plane, and S is the sigma in Greek. And then I say surface is sigma. Okay. What would the intersection be? A conic. What kind of conic? Z equals minus y squared. What the heck is z equals minus y squared? It's a parabola that opens down, and I should be able to draw that. If I'm not able to draw that, I don't deserve to be in this classroom. And then, let's see, for y equals 1, I would get z equals minus 1. If this is a square, if it's not a square, you forgive me, but it should look nice enough drawn on this wall. Many of you are engineers, of course, you take technical drawing or stuff, or you just, there's a lot of math lab. Don't judge me too harshly. Okay? So, this is what you would have, z equals minus y squared. I'm going to write on it. And how about I take y equals 0? I say I want y to be equal to 0 to make my life easier. No, to get a cross intersection between the plane y equals 0 and the surface sigma. What do I get? Another conic. What conic? Z equals 6 squared. Now, say, wish me luck, okay? All right. My hand was shaking, but it doesn't matter. So what I'm trying to draw, if I were to draw the other parabolas, these are not parabolas, they look like horrible things. But if I were to draw other parabolas, this you see the other ring, this you see, this you don't see because it's hidden. And then I'm going to cut. How did I cut actually? How do you think I tried to cut in my imagination? To get those parabolas. I tried to say, what if you take z to be 7? Or something like that. It's like having 49 minus y squared, and that's a parabola that opens down, but it's shifted 49 units up. And it's going to look exactly like that. So these guys, the blue ones, are along the x-axis that are coming towards you. I'm coming along the x-axis and I say, I fix x to be 7. And I do a cross intersection, I get this. parabola that looks like that. I go this way, the other direction, and so on. And different x values that are I set fixed at different values of x, I try to see what I have. I have parabolas opening down, opening down, opening down. 7 minus y squared, 9 minus y squared, 21 minus y squared, 700 minus y squared, all numbers like that. They become bigger and bigger. So, in the end, and I should be able to tell you what the rest of the picture should look like. In the end, what is this going to look like? I erase the scientific term of that, and I will give you a better feel of what you're going to have. Well, so guys, you don't see this edge. You have to have an imagination, otherwise you don't understand my pictures. This is like abstract Picasso's. This is the edge, this is an edge. I cut a patch, and that's another edge. And this is something you see, this is something you see, this is something you don't see, and I just do it like that. You see this part, and you don't see that part. You see this part. Maybe I can do a better job. Round it up a little bit, cut this patch with some scissors. What is this called? It's a saddle. It's a saddle surface. Saddle surface is the same thing as a hyperbolic parabola. And for one extra credit point, that you can turn in on half of a piece of paper or something, show that the surface z equals y is of the same type as the surface z equals x squared minus y squared. What kind of transformation should you consider? What type of transformation, parenthesis, coordinate transformation, should you consider? Now, there are calculators, graphic calculators like the TI-92 that can do about just as what MATLAB used to be able to graph such a surface. And if you graph z equals x squared minus y squared, you're going to get, what was the orientation? Something like this is the x-axis going towards you, the y-axis going in this direction, the z-axis is going up. How is the horse standing? The horse standing either in this direction or in that direction for the previous one. Z equals x squared minus y squared. Am I right? I forgot how we drew it. So, this is the y-axis. Okay, so suppose that I'm in the y-axis, I'm on top of the horse. The saddle point is the point where the Red Rider sits on the saddle. So the saddle is shaped like that. Longitudinally, you have it like that. Latitudinally, you have the other cross intersection going down. So my legs are hanging left and right. We are in that section. Now, if I have z equals xy, that's different. Is the horse, is the Red Raider looking straight forward like that and along the axis like I did before with this riding attitude? It's going to look different. You have to find that kind of transformation. What do you think it is? Or how do you think the surface rotation? And that very good. It's actually a rotation and a rescaling. Okay, it's a rotation and a rescaling. And maybe just to give you an idea, we still have a little bit of time. I know I shouldn't do trig in this class, But come on, how many of you do trigonometry? That was a long time ago, right? Wasn't it? So if I have, recall this type of transformation, this is just a here, okay? Suppose I am in plane xy. It was big in plane long time ago. And I'm changing coordinates and I'm saying x prime, y prime will be the matrix A. You didn't know that, but if you came here to the ending Notre Day, you would know because I did that in the ending Notre High School day. I explained how to multiply two matrices. You have a vector multiply to the left by a matrix of rotation. The matrix of rotation by 45-degree angles would be like that. Cosine of the angle, cosine of 45, minus sine of 45, whatever that angle of rotation phi is, sine of 45, cosine of 45. Let's see what the heck this change of coordinates is. Right? Do you guys remember what cosine of 45 was? Square root of 2 over 2. One of my friends and colleagues was telling me in Calc 1 that her students don't know that. You know that. I know that we don't remember everything, but every now and then we need a little bit of a refresher. Square root of 2 over 2 minus square root of 2 over 2, square root of 2 over 2, square root of 2 over 2. Oh my God, that was a lot of work. xy. How did I write it like that for the high school days? I did, because although they don't know how to multiply two matrices, I wanted to show them how a system of equations is actually linear system will be equivalent to this matrix multiplication. So what does this mean? If you take an introduction to C or some programming, when I took introduction to C++, this was the first thing they asked me to do, multiply with the rotation matrix. And it was fun to program something like that. So how is this going? X prime will be, you go multiply one row by a column. So row column multiplication means first times first plus second times the second. Root 2 over 2x minus root 2 over 2y. Now you don't have to pay tuition for the first two classes of linear algebra. Are you taking, and is anybody taking linear algebra at the same time? So you guys already knew that. But anyway, let's do that. Plus root 2 over 2y. Now, interestingly enough, there were some high schools where they teach matrix multiplication, and some high schools where they don't teach matrix multiplication in algebra. Okay, now, what if I multiply x prime and y prime? What do I get? What if I have z equals x prime, y prime? It's what kind of surface is that? Z equals, you're smart people. You should know how to do that. I'm running out of gas.
X over 2, x squared over 2, y minus y squared over 2.
Right. You're too fast for me. You're good. You're really good. This is a minus b. This is a plus b. So it's like it says product of difference and sum is the difference of squares. So it's like this a squared minus b squared. So, but he is also smart and he said, come on, Magdalena. He didn't say that, but that's what he meant. Square root 2 over 2 is much simpler than you say it is 1 over root 2. So this guy is x over square root of x over square root of 2. So when you square that was a lot of explanation. When you square that, it's x over square root of 2 squared minus y over square root of 2 squared. So z equals x squared over 2 minus y squared over 2. Oh my God, that was long. Alright, you've seen, I'm almost doing the extra credit homework for you. I want you to brush up the details. How would you get from such a surface where you have x prime, y prime to xy? You just rotate the axis of coordinates. The problem is I'm still getting this annoying and spiteful 2. Instead of getting z equals x squared minus y squared, I get z equals x squared minus y squared all over 2. What the heck does it mean? Can I do something about it? Well, yeah. What is this called? You can arrange that. What is this transformation called? Rescaling. How do you know these things? I just said it. Wow, you're like. So because rescaling is something that people in my area use a lot. In differential geometry, we talk about rescaling coordinates, rescaling matrices, but most mathematicians don't know that. So you're a good recorder. I'm going to absorb right away. Rotation and rescaling will do. So practically, when you multiply x and y in such an equation by the same number, it's like what I'm doing now. Look at me. So on the whole picture, assume you have z equals x squared plus y squared. What if I have z equals 9x squared plus 9y squared? I did a rescaling. What kind of rescaling? 3 times x and 3 times y, and I changed the coordinates. What's going to happen to my length, to the valley? It's going to stretch like that from here to here, but the shape is the same. The overall shape, the topology of the lamp is the same. Very good. Is there anything I wanted to teach you and I didn't teach you? Last time I taught you about some circular cylinder. I taught you about other kinds of cylinders based on other kinds of curves. Parabolic cylinders or other cylinders. What is a cylinder? I didn't tell you what a cylinder is, and I didn't tell you what a cone is, and we don't teach you in the book. But I'm one of the authors. But this is something that I would like to talk to you a little bit about because rule surfaces are important and we don't do them, we don't cover them in this course. And it's somewhere between vector calculus and analytic geometry, and I would like to know what a cylindrical surface is and what a conic surface is, because you're an honors class and you should know a little bit more about quadrics than anybody else. So, nice quadrics. Like z equals, what did we do last time? It was like x squared plus y squared equals 9, z equals y squared were discussed last time, and we decided that they are cylinders because, how did we decide? One variable was missing. And that variable can be considered to be a parameter. So what we said is that let's erase the circle x squared plus y squared equals 9. But z could be 0, 1, 2, that would be a discrete set of values, but it would be a continuous real parameter. So what I'm doing, I'm creating a cylindrical surfaces with the motion coming from the one family, one parameter family. So I'm describing a cylinder. The same way y is missing here, along the y, I can describe a cylinder. But how would I describe a cylinder in general outside of the chapter in the book? Could somebody tell me what's a cylinder? Cylinder is not a can, or it's not always a round cylinder.
Is it a prism with a
It's not a prism. Any surface that, okay, let me show you how I, in general, can I still have fun? I want to generate, you're going to catch it in a moment. I have a generating line, and I say, I want this line to stay, it's going to move along a curve, but it has to stay parallel to itself. Say what, Magdalena? Say it again. It has to move along a line, along a contour. Line doesn't mean straight line. Could be any curve. But it could be at an angle, but it has to stay parallel to itself while moving. So I'm going to go and start moving it. I have described a cylindrical surface. You see how it stays parallel to itself? Okay, so a cylindrical surface cylindrical surface is a surface, is a full surface generated by the motion of a line, of a straight line, along the curve, which remains parallel to itself. And I'll try and draw. I didn't like my handwriting here, okay, you'll excuse me. I think sometimes pictures, that's why I have to draw. Pictures are worth a million words. So this is the plane. This is a regular curve. It could even have self-intersections, it doesn't matter. And I'm going to have a motion, continuous motion, of a line that stays parallel to itself. And it describes a cylindrical surface. And you say, hey Magdalena, but excuse me, but this surface crosses itself. And so what? Sometimes surfaces have cross intersections. So that surface will look like that. Right? You see, it's the surface described by my arm. It could be a curve that's much nicer with no self-intersection. It's still a cylindrical surface. What's a conic surface? And that is the last thing I want to do. And before I say that, you know what I want to say, keep your thought. Before you go home, what do you promise me to do tonight? Not tonight. You have the whole weekend, thank God. To do that, you have to do tonight. Friday, Saturday, Sunday, a little bit every day, 1 hour, 2 hours every day. I'm also a student. I'm taking some classes on life sciences. For the first time in my life, I'm 48. I decided that it's time for me to learn some anatomy, physiology, chemistry, biophysics, protein biology, stuff that I've never studied. And it's a little bit related to the mathematics and geometry I'm doing research on. Then I got into this a little bit more. So now I'm taking a class on stress management, which is very interesting because I realized that I have no idea how to manage my own stress. And all my life I made mistakes. And now I'm taking this class. And we have homework twice a week, Tuesday and Thursday. It's so hard. I promise, I'm not going to be doing such a... It keeps me on my toes. I want you to stay on your toes, but I'm not going to give you homework that's do that often because it's really doesn't let you do anything else. Alright, so you have Friday, Saturday, Sunday to go over those examples in the section 9.7. Read them. No homework yet on web work. Sunday you're going to get your first web work homework. I don't want to overload you. The class, one of my classes is about research, medical research based on mathematics and statistics also. The other class is stress management. And I was thinking this class is about stress management, but the class in itself may stress me out a little bit more than anything else because the homework comes so fast. I mean, having homework twice a week in every class, how do you manage to have a job and do your job well? I don't know how to do that. It's practically impossible. But I go to bed at 1, so it's not 1:31, wake up early, and I hope to survive. About the conic section, what do we have? The conic surface, sorry. Conic surface. Could anybody tell me by analogy, and I think Alexander is ready to tell me what the conic surface would be? It's a surface. Shall I write down? I feel so, I should write down. Although I'm what do you think that is? I'll take it slowly. Is it a ruled surface or not, in your opinion? Yes, it is. It's a ruled surface. Why do I put ruled in parentheses? Because it's a little bit like an oxymoron. When you say, what's a ruled surface? It's a surface generated by the motion of lines. So since I already say that it's generated by the motion of a straight line, saying it's ruled, it's saying the same thing twice. Right? So it's a ruled surface generated by the motion of very good of a straight line along the curving plane. Which passes through a fixed point, through a fixed point. Okay, so have you ever heard the notion of the name pencil of lines? Pencil of lines. I have discovered, I was teaching 3350 last semester, and I came up with this equation, differential equations you don't know it yet, you'll learn it next. The family of solutions of that equation was of the type y equals kx, where k was a real parameter. Real numbers, non-zero. Okay? What is this if you draw that in a plane? Y equals kx will be a pencil of lines. I didn't know that 15 years ago it was called pencil of lines. And now I know. So, different slopes, the slope is k. All of them, all the lines, pass through the origin. So it's a family contained all of them, except for, well, if you put k equals 0, then you also have y equals 0, which is this. Okay. What is a pencil of lines in 3 dimensions? It's a family of lines that passes through a fixed point. Of all these lines that are like the radii and radius, so you have like the sphere, and you have like all the radii that's coming from the center of the sphere, okay, in all the directions. From all of them, you only take those lines that intersect the given curve. That is a curve. And you have here 2 conditions. Your straight line, give me a name, little l. L intersects big L, different from void. What does this mean? That little l has to touch big L. And little l passes through P, which is fixed. And what you get is a conic surface. It's a cone. Okay, it's also a ruled surface. Is there anything else I wanted to tell you? Not for the time being. I think I have exhausted everything I wanted to teach you about conics. I told you about conics and quadrics. I taught you a little bit about conics last time. I showed you a few quadrics, showed you a lot of quadrics today. This is not over. Do you allow me to disclose our secret to everybody? Okay. We have that secret website. The University of Minnesota has the gallery of quadrics. Did you find it entertaining and useful? And once you go over those pictures and play with them, it sticks. You remember those names for the surfaces and what they look like, and it's going to be a good start for the next chapter. Tomorrow, I'm going to send it to you, I promise. No. It's just, I'm going to make it up. By email, I'll send it to you. We'll be there today on the phone. And I'll see you Tuesday, and Tuesday we'll start chapter 10. And that's about it. You're going to have some homework from web. Any questions? Yes, sir. No. After they put me through this, I promised I would never put you through this. The homework will be doing minimum 7 days, maximum 2 weeks. Depending how long it is. You can go ahead and turn in the